Hi friends, in this video I'll be telling you how to calculate the effective capacitance when you have a combination of capacitors, as well as how to calculate the energy stored inside a capacitor. We'll start with series combination. Say you have two capacitors connected in this way in series. Of course, both are different capacitors having different capacitances, but note this point: whenever capacitors are connected in series, the magnitude of charges on the plates will be same. This is plus q and this will be minus q. This will be plus q again and this will be minus q. Now the potential difference across these two endpoints A and B can be written as the sum of potential drops across these two capacitors. Say let the potential difference across this capacitor be V1 and this be V2. Now V1 plus V2 is my potential difference across A and B. Now for this capacitor, first capacitor, you know that capacitance is Q by V, so I can write V as Q by C, right? So V1 will be Q by C1. Similarly, V2 will be Q by C2. And if my net effective capacitance is C, the charge will be the same, right? So I can write V as Q by C. Now we have Q by C is equal to Q by C1 plus Q by C2. If I cancel this Q terms, I get 1 by C is equal to 1 by C1 plus 1 by C2, where C is my effective capacitance. And if this is the case with two capacitors, if I have many capacitors, I mean for n capacitors, the formula will be 1 by C1 plus 1 by C2 plus till 1 by Cn is equal to 1 by C, where C is my net effective capacitance. This is the formula for calculating effective capacitance when you have series connection. When you have parallel connection, say you have two capacitors connected parallelly in this way. Now these are my two endpoints A and B. Let the capacitance of this be C1 and this be C2. Here the charges on each capacitor are also different. Let the charge on first capacitor be Q1 and this be Q2. Now if I want to replace this system by a single capacitor which has the effective capacitance C, then it should be able to hold the charge which is the summation of both these charges. I mean the effective capacitor should be able to hold a charge of Q1 plus Q2, right? Now we know that Q is equal to CV, and this Q, my effective Q, is nothing but Q1 plus C1. In other terms, I can write Q1 as C1 V1. Actually there is no V1, there is only one potential difference. Okay, then Q2 will be C2 V, and my net charge is also CV, where C is my effective capacitance. So if I cancel this V terms, I can write C is equal to C1 plus C2. It is just the algebraic sum. When I have n capacitors, the net capacitance will be C1 plus C2 plus C3 still Cn. And this is the formula when you have n capacitors connected parallelly, and it even makes sense, right? Because if you have two capacitors having plates separated by equal distance and connected parallelly, see, this distance doesn't matter to me, so I can join this and say that it appears to be a single capacitor having a much bigger plate. I mean the area got added algebraically, so the capacitance in turn should be added, and hence it makes sense. However, leave it. Let's move forward. Let's solve a problem here. This is capacitor 1, capacitor 2, 3 and 4, and I want to replace this system by a single capacitor across these points A and B. I mean I want to calculate the net effective capacitance. You see this C1, C2, C3 are in series connection, so the net effective capacitance of these three capacitors will be C dash, which is 1 by C dash is equal to 1 by C1 plus 1 by C2 plus 1 by C3, and this C dash and C4 are in parallel connection. So my net effective capacitance C will be C dash plus C4. And from this formula you can write this one as C1 C2 C3 by C1 C2 plus C2 C3 plus C1 C3 plus C4. So this is your answer. Let's move forward. Energy stored in a capacitor, or I should say the work we need to do to bring the capacitor into its charged state. So what I'll do, you know that the work need to be done here is for transferring the charges from one plate to other. So I'll transfer small charge elements dq from the plate on the right side to the plate on the left side, so that finally my charge on each plate becomes q and minus q. So now see, at any instant, say the charge on each plate is q dash, and here it will be minus q dash. Now I'll bring a small positive charge from here to here in this direction. Say that is dq dash. So here the charge increases and here the charge decreases by the same amount. What is the work done to move the small charge only? That will be potential difference into the charge, right? But the potential difference is varying here continuously because the charge is varying. At this instant, the potential difference is say V dash, and the charge, as you know, is dq dash. This is the work, right? This is the this is the work need to be done for moving this small charge element. But this is a capacitor. Note that for capacitor, at any instant or at any instant of time, we have this relation C is equal to Q by V. So I can say that V is equal to Q by C. Hence I can replace this V dash term with this Q dash, which is the charge at that instant, by capacitance. And here I have the relation in terms of Q dash. So to find the net work that need to be done to bring the capacitor into the charge state, I'll just integrate here. Here Q dash is a variable, so the net work becomes Q dash square by 2C, and the limits are, the final charge is Q and initially the charge was 0. Hence you integrate it, you will get it as Q square by 2C. This is the work that needs to be done to bring or to charge the capacitor. Now there are other forms of writing it, because you know that Q can be written as CV. So the same W becomes Q square by 2C, which is nothing but half CV square in terms of C and V, and the same thing can be written as half QV in terms of Q and V only. And note that electrostatic force is also a conservative force, and so this energy is stored as the potential energy, and this potential energy is stored inside the electric field. I mean to say that in the region between these two plates. So I will introduce you to a new term. You know that the net energy is this thing, right? And I'll write C as A epsilon naught by D, and I can write V as electric field into the distance. You have the square there, so we'll write it like this. This is the net energy, but there is something called as energy density or energy per unit volume. What you have to do to find it, you have this total energy, half A epsilon naught by D, E square D square. You divide it with the volume, which is nothing but A into D. You get these terms cancelled, and finally you have this energy density U as half epsilon naught electric field square. Now let's try to do a small problem. You have a 900 picofarad capacitor which is charged by 100-volt battery, and I have to find the electrostatic energy stored in the capacitor, which would be half CV square as I explained before, and put the value of C as 900 into 10 power minus 12, and V square will be 10 power 4. This will give you the answer as 4.5 into 10 power minus 6 joules. Well, now what if I remove the battery and connect another capacitor which is having the similar capacitance. I mean, this will be a new situation. After charging it with a 100-volt battery, I remove the battery and put another capacitor here of same capacitance. Now, initially the charge after charging with the battery was Q here. Now some charges get transferred from this plate of capacitor to the bottom plate in this direction. So note this, since they are connected by wires, the potential on this point, at this point, this point should be same because it's a conductor, right? Similarly here also. So the potential difference V dash across these two capacitors is the same. And I said that the capacitances of these two capacitors are also same. Hence the charge on these two capacitors should also be the same. Before it was Q, some charge gets transferred and hence the new charge becomes Q by 2 here, and here also it becomes Q by 2, and here it will be minus Q by 2, here it will be minus Q by 2. Hope everything is clear till now. Now we know that C is equal to Q by V. C is a constant here. So since charge is halved, you have to say that potential is also halved. So my V dash is nothing but initial potential difference divided by 2. As we know, the new charge Q dash is Q by 2. Now on each capacitor the energy stored is half QV, I mean half Q dash V dash, and there are two such capacitors, right? So the net energy of the system will be this one, which is nothing but Q V by 4, because Q dash is Q by 2 and V dash is V by 2. Now before, the situation was something like the energy was half QV before connecting this new capacitor, and when the battery was there, this was the energy, and now the energy is QV by 4. It has been reduced, actually it is halved. Now where has this energy gone? I'll tell you where it's gone. I said that some charges get transferred from this plate to this plate in this direction, right? And even the same thing happens here also. During this process, I mean, when charges move through a conductor, you get some current. I'll explain you in detail in the next chapter, current electricity. But when charges move inside a conductor, you get current. And when there is a current, you can say that some amount of energy is lost as heat or electromagnetic radiation. However, the other half of energy, the other QV by 4, it's lost. It's lost as heat to the environment. It can't be regained. And hope everything is clear till now. And that's it, friends. Bye.